Good morning, ladies and gentlemen. Welcome to our company's presentation at ACI Convention Fall 2023 in Boston. My name is Jiří Remesh and I will be talking about our software called Atena, which is used for advanced modeling of reinforced concrete structures. For those of you who are not familiar with our company, we are providing software solutions and consultancy services in the field of concrete engineering. Our main product called Atena is made for obtaining the actual and realistic response of reinforced concrete structures and reinforced concrete elements. And the fact that we aim at obtaining the actual and realistic behavior of concrete material and concrete structures is also expressed in our company's motto: test your structure before you build it. Let me start with a little bit of the background and motivation for what we do. In the field of concrete engineering, most of our understanding and most of our design formulas, they are deduced from simple laboratory experiments. You can see here bending of a slab, bending of a beam, punching shear of a slab or a shear wall subjected to monotonic or cyclic loading. And this is quite natural, because if we study something in the laboratory, we want to focus on one thing, one loading mode, and then based our formulas on this simple loading scheme. However, in reality, we often have to deal with more complex and more difficult situation. For example, here you can see steel beams embedded in massive concrete, which will result in complex stress state around the place where it's embedded. There might be some stress concentration, etc. Or nowadays there are many very beautiful but ambitious architectural designs, such as shown here or here. Of course, there is this new technology of concrete 3D printing, as shown here and here. And now, when you look at these examples, they are much different from the simple laboratory tests, and therefore we need some additional tools which can provide us with some insights into the behavior of these structures. So, if we want to model this, and if we want to really focus on the actual response, we need nonlinear material models. These models should be able of capturing the material response in form of cracking under tensile loads or crashing under compression. In our case, this is done by deconvoluting the strains or decomposing the strains into elastic, plastic, and fracture part. And when we talk about this, the plastic strains, they are taken into account when the concrete is subjected to severe compressive loads and starts to crash. And in this case, we use the plasticity approach with linear softening. When we talk about tensile branch, when in the material the maximum tensile strength is exceeded, we assume there is crack formation using a smeared crack approach with a crack band. And the softening branch after the maximum tensile load is based on the fracture approach and is simulated based on the amount of dissipated fracture energy during this process. Similarly, for the reinforcement, we can simulate yielding, and even if the maximum and ultimate strain is obtained in the reinforcement, we can simulate rupture. This is done by prescribing multilinear stress-strain relationship in the model. The question is how this approach, how this finite element nonlinear simulation can be used in real practice. For this, it's the best thing how to check it is to compare it with experimental data. And one of the best thing how to do it is to participate in blind test prediction. In our company, we have long tradition of these kind of predictions. They are usually organized by some well-known university, which in advance send out details about the test they will conduct, and the participants in the competition, they provide their estimation of the experimental behavior. And after that, the university collects them and conducts the actual experiments, compare the predictions with the actual results, and then announce a winner. One of these tests, one of these competitions, which I would like to mention here, is the one from 2015, conducted at University of Toronto by the team of Professor Collins. It consists of a large beam subjected to shear loading. You can see that the loading was a little bit off the center, meaning that on the left side there will be a larger shear force than on the right side. However, also the reinforcement differed. While on the left side there was shear reinforcement provided, the right side of the beam was unreinforced. And if the beam would follow the standard valid at the time, it should first crack on this left side, because there was a larger shear force. However, and that was something they wanted to show in this competition, in reality the crack occurred on this right side. On the bottom, you can see the result of our simulation, which we provided for this blind test prediction. Now you can see development of tensile cracks, which will soon start to connect into a shear crack. You can see that the shear crack is now forming on the right side of the beam, resulting in the failure. In the actual experiment, after the failure was obtained on this right side, they constrained the beam and continue with the loading on the left side to also obtain failure there. Therefore, with one experimental sample, they managed to obtain 2 experimental results. And also, this was simulated in the numerical prediction, and because our prediction on both sides was very close to the experimental results, and also the crack pattern matched well the experiment, we were announced as the winners of this blind test prediction. Here you can see just schematically our other benchmark blind test prediction which we participated in, and more of them are summarized in this table. The green dot represents our prediction, and you can see that it's in most cases quite close to the actual results. This means the actual experimental results are shown here as 1, and the range of other participants who submitted their prediction is represented by this gray error bar. So you can see in many cases we are close to the actual experimental results, and with exception of few cases, if the prediction was not so good, it was at least on the conservative side. When we want to apply this nonlinear analysis for real structure, there are some differences compared to traditional linear approaches. In traditional design, we usually analyze the structure to get the internal forces in the elements, and then we check the critical cross-section if they can resist these forces. For example, if I have a structure like this, I would be probably checking the column here for the compressive strength with combination with the bending moment. Then the beam over here, I would be checking the shear force at the ends, and in the middle I would be checking the bending moment. And if all the cross sections can satisfy the design condition that the resistance is larger than the effect of internal forces, then I can say the structure is safe. In the nonlinear approach, I simulate the whole structure, and basically I'm checking all the cross section at once by this global approach, and I will be checking the global response of the structure, and if all the loads if I can reach to the load level higher than the design load level, and the structure can still withstand these loads, then I can say that the design is safe. This approach is now included in design codes, at least in this FIB model code, and it will be introduced in the new generation of Eurocodes used in Europe, and probably same thing can be also done based on the valid ACI codes. Of course, as I mentioned, the match with the experimental results it's not always perfect. There is always some uncertainty. One source of this uncertainty is that usually only one parameter is provided for the modeling, which is the compressive strength, while in fact for the nonlinear material model we need several parameters, and these are all based on the provided compressive strength. So one source of the uncertainty comes from this fact. Another thing is that it's still a material model. It's not perfect. So there is some uncertainty in the possible underlying mechanism for different materials, for different concretes, etc. So in fact, if this uncertainty is specific for each material model and each software. For Atena, it's 1.16, meaning that we should have at least 16% margin in the structural resistance in order to be sure that the structure will be safe. Let me now go to some examples. I will be showing examples of two bridges. One will be checked for ultimate limit states as well as the serviceability limit state, and the other one will be checked for its durability and how its load bearing capacity reduces over the time due to the chloride attack. Actually, in Atena, there are several features which are aimed specifically for the engineers dealing with bridges. This is summarized in this slide. For example, the reinforcement can be simulated both as discrete or shear reinforcement. Similar elements can be used when simulating pre-stressing tendons. For the concrete material, we can use 3D solid elements either with linear or quadratic approximation. And for some regions with quite clear static behavior, we can use some simplified elements to speed up the calculation. These elements can be either shell or beams. So let me go to the first example. This is a pre-stressed girder box viaduct with a span of 48 meters, and the height of the box girder is 2.7 meters. And the fact or the reason why we conducted this simulation, or why we were asked to provide to create a model and provide provide the result, was the fact that during the construction phase there were shear cracks developed in the web of the girder box. You can see it here on this photograph. This actually happened during a prolonged construction break when the structure was subjected to the temperature impacts. So when we run the simulation in kind of complex way that we also included the construction period with simulated the balanced cantilever construction method, then press stressing of the left span on the right span to create a continuous beam, and then when the bridge was still unfinished, we prescribed the thermal loads according to the on-site measurements. And at this moment, we were able to reproduce the cracking which occurred in reality. You can see that in the model, the crack they form at the same place as on the real structure. You can see them going from the web of the box girder and then coming to the bottom side, same as in reality. So the operating authority then decided that there should be some strengthening measures provided. So we also simulated this in order to estimate how they will be beneficial and how they will impact both the ultimate load-bearing capacity and the crack width. So here you can see the strengthening. It was in form of additional pre-stressing cables in the girder box, and here you can see the obtained results in form of a load displacement diagram. You can see how the load is gradually increased during the analysis, gradually adding the dead loads, also the live loads, also simulating the settlement of the support and the thermal loads. The unit load with the design load combination is indicated here at load level 1. And after that, we kept increasing the load level to obtain the load level 1.16, which is including the model uncertainty. And after that, we can say that the structure is safe. You can see that soon after this level, we observed in the model yielding of the reinforcement bars. Actually, this is for the left span when the loading was introduced. However, according to the design procedure, this was not the ultimate load-bearing capacity. It was reached over here when we observed the ultimate strain in the concrete actually under compression. So this point was taken as the maximum resistance of the structure. It exceeds the required combination, so we can say that the structure satisfied the required design. After that, if we kept increasing the load, we observed yielding of the additional pre-stressing cables, and the structure goes into very like plastic behavior, almost reaching the peak load. Then we also simulated the impact of the additional pre-stressing on the existing crack weight. Here you can see the crack weight before the strengthening. It was approximately 0.75 millimeters, and after application of the strengthening, that you can see that the cracks, they close and they generally go below 0.4 millimeters. So this was required by the operating authority to check also the serviceability of the structure. Another example is a bridge in Germany. You can see the whole bridge structure on the photo on the right. We focus on two spans in this location. It's a reinforced concrete bridge with a span of approximately 14 meters. And in this case, we actually applied our durability model, which starts with the mechanical model as shown in here. It uses the crack weight from the mechanical model as an input for mechanochemical model. This mechanochemical model can calculate the chloride diffusion, taking into account the acceleration due to the mechanical cracks. And based on that, it can calculate reinforcement corrosion when the critical chloride concentration is reached at the depth of the reinforcement. Then it it assumes that the reinforcement starts to corrode, it reduces its cross-section, and updates the cross-section diameter in the mechanical model, calculates new static equilibrium, new crack width, and by continuing this approach back and forth, we can assume how the crack width and how the model will behave in the long term, and we can assume how its mechanical performance will decrease over the time. This is somehow summarized in this slide on a simple example. You can see a L-shaped beam with mechanical cracks in this location. These mechanical cracks, they accelerated the chloride diffusion, which results in higher reinforcement corrosion in this region compared to the region over here. In the case of more complex structure in here of the bridge, it's shown in this slide. You can see the chloride concentration at the reinforcement depth in here, and again in the location with the mechanical cracks, you can see that the chloride concentration is larger compared to the rest of the structure. This results in a higher corrosion degree in this region, and of course this will result in higher stress in the reinforcement and larger crack width in this region. Finally, if we simulate it for 150 years, in this model we observed large increase in the midspan deflection, leading to the collapse of the structure. To provide some quantitative information, it's possible to obtain the load displacement diagram for a different duration of the chloride attack. This is shown in this slide, and you can see the load displacement diagram for different duration of the chloride attack. This is the model with the mean material parameters used for the material. These load displacement diagram, they give the data points on this curve, showing the decrease of the resistance over the time. If the same thing is done with the characteristic material parameters, then it's possible to calculate the design load resistance based on the ECOF method. This is one of the methods which I was showing earlier. It's based on the FIB model code, and based on these two analysis runs, one with mean, one with characteristic material properties, it's possible to obtain the design resistance of the structure as a function of time. Now I would like to briefly introduce our capabilities in the field of modeling of 3D concrete printing process. In this field, it's possible to use the software to reproduce the laboratory experiments and then upscale them to new shapes, new printing speeds, new environmental conditions such as humidity, temperature, or we can simulate the wind loading on the freshly printed structure. Our approach is that we create again a finite element model, and then we gradually activate the elements along the printing path. Each element has different construction time, and this construction time actually governs its material properties, meaning that at each step, each element has different compressive strength and different other parameters of the material model, and by this means we can simulate how the material hardens, and if the load and the printing speed is too high, we can simulate progressive buckling collapse. Actually, this analysis can be done now based on the standardized G-code input, which is used by the softwares for modeling of the 3D printing objects. This can be directly loaded in Atena, it can create the mesh. This mesh can be then constrained, and it can be prescribed a material model, and then we can directly conduct the analysis. For the material model, we now have an approach how to derive the mechanical properties based on the underlying hydration mechanism of the fresh paste. We start with the hydration curve. This is very beneficial because then we can easily upscale it to new temperature, for example, accelerate it when the temperature is higher, or we can easily calculate how the hydration will run at lower temperatures. Based on the degree of hydration, we calculate the compressive strength and then deduce all the remaining parameters of the material model based on the compressive strength. Here, this is an example. This is a simple laboratory test of a cylinder being printed until the collapse is observed. You can see that the Atena results quite well agrees with the experimental value. And now I would like to show you one last example of this concrete printing. This is a house. Actually, it's the first 3D printed house constructed in the Czech Republic. It was printed in the city center of Prague, of our capital. Firstly, I will show you something from the construction because there was another, like a twin brother of this structure, printed in the laboratories of the Czech Technical University when they subjected it to loading to test its load-bearing capacity. You can see the construction process, and now this is from the loading. In our Atena model, we focus on modeling of the construction process. You can see now how it's being modeled, and the colors, they show the location of the plastic deformation, somehow showing the damage in the material due to compressive loadings. You can see that at the bottom there is not much of the damage. However, on the sides, because the printing pad was shorter, at the bottom they printing the whole length. In here it was just going over here and then returning back, so the printing speed is approximately double, so you can see some damage accumulated there. And of course the highest damage would be on the top of this opening, because it was only self-supported due to the arching effect. So of course we can understand that there might be some damage due to the printing. The Atena software also predicted cracking in this region. Finally, we compared the initial printing speed with some accelerated construction method. You can see that if they increase the printing speed, they might expect a buckling of the wall at the fresh state and collapse of the structure. So this was somehow like a parametric study to see what will be the optimum printing speed. Another application of Atena can be in nuclear industry, for example. This shows a containment structure with the opening, and it can predict the cracks around this opening along with the stresses in the reinforcement. It can be used to new types of strengthening. Here it's an example of a beam strengthened by the FRP sheets in the midspan. Or one last example, this is application in massive concrete structures when this is not a static analysis, it's transport analysis, and it also uses the hydration curve to calculate the heat which would be released due to the hydration, and the subsequent temperature distribution in the fresh concrete, because often we need to check whether the maximum temperature stays under some certain defined limit. So with this, I would like to thank you for your attention. I hope you will visit us at our stand, at our conference booth in the exhibition area, where we can discuss the specific problems and specific projects where Atena can be helpful for you. Thank you again for your attention, and goodbye.
Atena program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name Atena. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.